So a topic that's come up quite a bit actually for many years now, but one that I'm working right now on with some data for a manuscript, and I have a bunch of other data collected on this. Lots of significant amount of publications around about this is the relationship between muscle oxygenation and maximal lactate steady state. Now there's a series of publications out there on NIRS signal and lactate breakpoints. We're publishing a paper, should come out pretty soon on that. There's a paper by Bruno Grassi and colleagues, 1999, I think so. So 2 decades back that showed there's a relationship there. There's this paper by Bellotti, I believe, and they do specifically maximal lactate steady state in NIRS. I can put up a figure here that I have of theirs, and they just show that this that finding basing a plateau in your deoxyhemoglobin signal during interval exercise that relates to maximal lactate steady state, or that correlates to maximal lactate steady state, that intensity where that initial break happens, that we see here in these examples from the paper. So, and this makes sense. So if we consider a recent paper by Brooks and Brooks' general work on the relationship between mitochondrial respiration and glycolysis, where lactate plays this role as fulcrum between the two, basically linking mitochondrial respiration and glycolysis. So the two are interlinked, making this whole aerobic system. So it makes sense that there's a relationship between lactate and muscle oxygenation. Now, specifically, just for the point of maximal lactate steady state, for people who are maybe not so clear with this term, lactate that we measure in the blood, which is typically the lactate we talk about, blood lactate, is the end product of the appearance of lactate and the disappearance of lactate. So how lactate is produced in the muscle and how it's cleared in the muscle. And once those two things, the end result of those two things together playing in an interplay is what we measure in the blood. And we don't really know, well, how much we don't know the total amount of lactate that's being produced in the muscle. We just know what is being produced, and in relation to what has been cleared, and that's what we measure. Maximal lactate steady state is kind of the maximal steady state performance that we have, that where this appearance and disappearance are somehow in a balance. And if you go above this, then lactate is just going to continuously increase. There's going to be more and more appearance versus the clearance rate versus the disappearance until exercise intolerance, basically. And so I have some data from ours. We did here with 10 subjects, and we did incremental exercise tests, and we got their ventilatory thresholds. So the ventilatory threshold 2, so respiratory compensation point, and we made them exercise constant load at ventilatory threshold and then minus 20% of ventilatory threshold. The idea being that if you look at literature, generally speaking, ventilatory threshold is kind of at the higher end of this threshold 2, of this gray zone of thresholds that make up threshold 2. And maximal lactate steady state is also one of those thresholds where they should be somewhat related, but they don't seem to coincide, or they don't seem to, that they're not different, but they're not equal. Statistically speaking, that's what often happens. Critical powers in there too. So there's this gray zone that make up this transition from heavy to severe exercise, so this threshold 2. And so we did ventilatory threshold and then minus 20 to kind of see where maximal lactate steady state sits. And we see in our data here that at ventilatory threshold of our 10 participants, actually one participant, but we only have data up for the first 15 minutes. So each data point is at the 5-minute mark. These are means. So we only have for about halfway through, and then people became exercise intolerant to a ventilatory threshold. And you see that lactate kind of increases, and it increases all the way throughout. So obviously above maximal lactate steady state. For the minus 20%, we get the whole 30-minute duration completed, and you see lactate, yes, it goes up initially, but you kind of find something like a little bit of a steady state. It kind of moves up and bubbles around a bit. So it's closer to something like a maximal lactate steady state. Now the question is, what does NIRS do during this? So we take the SMO2 raw signal. We see that there's an initial decrease in muscle oxygenation with increase in lactate at the beginning, actually for both the ventilatory threshold constant load and the minus 20% constant load. But you actually have a bit of an increase over time with the minus 20% into, let's say, a steady state of muscle oxygenation. Whereas you have a continuous decrease in muscle oxygenation through the first 10 minutes or so, and then with a slight increase towards the end on the absolute value of the means there. What's much more interesting, because the relevant point here is steady state, and so and the idea being that these thresholds in muscle oxygenation are more related to something like the rate of change of muscle oxygenation rather than the absolute value. So if we plot this as, well, how's muscle oxygenation changing? So what is the rate of change? And put this up in percent per minute. And what we see is that with lactate increase, we get a decreasing rate. So we get a negative rate. If you have the solid black line is 0. So anything below is a negative rate. We see you have a negative rate for both, but then in the minus 20%, that by the 10-minute mark, you actually have positive rates. And they actually essentially stay somewhat positive around the 0 mark all the way through exercise. So some kind of a balance in this oxygen supply and demand parameter of rate. So oxygen out. But what you see when you're over maximal lactate steady state, when you have ventilatory threshold, where lactate just goes up and up and up, you see that you have decreasing rate, and you actually have always a negative rate throughout the entire time. Even now, so you have the most negative rate at the beginning. That's kind of a response to exercise, something like VO2 kinetics, right? You have the system needs to get engaged first, but it remains negative throughout. Even at the very end, you're still slightly negative to failure. So kind of something like this plateau that's reached in the HHB and the deoxyhemoglobin plateau. So it just kind of bottoms out at the bottom where it probably can't get too much lower anymore. Nonetheless, the rate's negative the whole time. The idea being that negative muscle oxygenation rate is indicating a non-steady state, whereas kind of a zero slope, a zero rate, or a positive rate is something more like a steady state that's maintainable, and that's reflected in the blood lactate, or muscle oxygenation reflects blood lactate, chicken and the egg, whatever you want to take first, which is quite nice. So just something to comment on, and that I've talked with a few people on. Thank you for listening.